Hello, guys. Welcome back to MedZone African Motives. We are still on our engineering science N4, and this is August 2023 exam that is working on the hydraulics. So this is a question based on hydraulics. So we are given 5.1. The following data refers to a single acting press. So take note there. We are dealing with a single acting press. All right. So given the piston diameter, the piston stroke, that is the ram diameter, the slip, then we're asked to calculate the actual volume of the liquid per stroke and the distance and this and that. All right. So I'm gonna have this here from the information that we are given. This is the piston diameter. All right. Then we've got the piston stroke and also the ram diameter. Right? So the piston diameter, meaning to say we are talking about a simple, this is just a simple hydraulic press that you're given. All right. So thus we have got the diameter of the ram in this case, which is 80, this one. I mean, from the plunger side, this one, or 80 millimeters divided by 1,000, that's 0.08 meters from the plunger. Then the piston stroke, which is the stroke length, is given as 120 millimeters, which is 0.12 meters. That is our stroke length. Then for the ram, we've got the diameter of the ram in this case, that's divided by 1,000, 0.35 meters, and also the slip. Remember, from the slip, what we obtain here is the efficiency. Efficiency, it's 100% minus the slip percentage, meaning to say we are going to subtract 12% from what? From 100% in order for us to obtain the efficiency, and that is 88% efficient. So here we are given the efficiency of 88%. All right. So I don't know, because of the time, maybe when and are we going to have this class uploaded? But if you are to check, I have managed to work on the introductions of each and every part, working with the hydraulic press, working with the hydraulic accumulators, working with the hydraulic pumps, each and every part that you need to know in your syllabus. Okay, so I want to explain this, and I explained actually in this manner, and we have some of the formulas from our formula sheet, the way they are given. But I explained this, like I said, I do not know what is going to come first on the uploading of the videos, but this is what I explained on the on this part of the efficiency. All right. Considering that we are given the information of the efficiency, it can be used depending with what you are given or what you are supposed to calculate. The efficiency can be taken from the work, it can be taken from the power, it can be taken from the way the force, it can be taken from the effort that is being applied. So it depends with what is to be used later on. All right, this is not part of as the question here was the actual volume. So in order for us to have the actual volume of the liquid per stroke, what are we going to do in this case to have the actual, because we need this from the efficiency. So the actual volume, this is going to be affected from the efficiency. All right, we are going to take this from the efficiency. And I explained this in 2 ways, right? I explained this in 2 ways in order for you to obtain this VRAM, which is the actual volume that we have. One, we can use this formula from your formula sheet here. There is a formula that this one here. All right, take note. We have got this formula here. We do not have the mechanical advantage in this case. Take note, this one is not working. This is not on a single acting hydraulic press whereby there is an effort which is applied on the lever and whereby we've got the force of the handle. No, we do not have that. This is the one that we use, and on that part, they will give you the mechanical advantage. What we need is to understand from this formula, the way that is given here, it is Vs is equal to Va times 100% over N. What is this formula, or what is it representing? This is the formula that is simply taken from this efficiency that I explained as this way. The efficiency is equivalent to the volume that we have on the RAM, that is VRAM over V plunger. That is the case. So when the efficiency is involved, it means we are now calculating actual values. So in order for us to have VRAM in this case, where as we can see here, we can just multiply this side. We can just make VRAM the subject. This is same as over 1. So it's going to be efficiency times VP for V plunger. Then we divide by this 100 divided by 100 is equal to VRAM. All right, that is the volume on the RAM, which is the actual volume. That is our actual volume, is equal to the efficiency times VP over 100%. All right, so that is what you're going to have. If you are taking this from a simple, this is just a simple hydraulic press that you're talking about there. All right. So we have, or where are we going to have VP? That is the question, because once we have VP, then it means we can calculate VR. VP can be calculated because we've got this, the diameter and the stroke length of the plunger. So from the plunger side, remember the volume is equal to the cross-sectional area, that is pi d squared over 4 times the cross-sectional area times the stroke length. All right. In this case, we are not given the number of pumping strokes, so it's just going to end here. All right, so that's pi times the diameter on the plunger, 0.08 squared over 4 times the stroke length. We are given there the stroke length is 0.12. So this is going to give us, in this case, if you are to use the number of strokes, it's going to be just 1, because they are saying here it's the volume of the liquid per stroke. So if you are using the number of pumping strokes in this case as N, we're just going to multiply by 1 per pumping stroke just by 1, okay? So it does not affect anything, all right? So this is going to give us the volume of 6.0385, something like that, which is 0.32. So it's going to be 0.32 times 10 to the exponent of -4 in cubic meters. So with this, this is an ideal value, because we do not have the efficiency there is not applied. So in order for us to have the actual values, we have to apply the efficiency in order for us to have VRAM, which is the actual value once the efficiency is involved. So that's our VRAM is going to be the efficiency. Remember, our efficiency there was what? Our efficiency was, 88%. So that will be 0.88. Just because we've got the 100 here, so we're just going to write as it is. So it's going to be 88 times VP, which is our VP. We got this as 6.032 times 10 to the exponent of -4, everything over 100. So that's our VRAM in this case, which is our actual volume, which is going to be 5, when I have something like 5,3087, 3081, something like that, which is going to be 308 times 10 to the exponent of -4 in cubic meters. All right. So that is how we could have calculated the actual volume. If we had a condition when it is when you have got the effort, make sure that you watch the videos of the introduction part. We talked about, check on the single acting hydraulic press. All right, that's where I explained much on that part. Okay, then here they want the distance that the ram has to move after 15 pumping strokes. All right, after 15 pumping strokes, what is going to be the distance that the ram moved? Remember, the distance moved by the ram is represented by H. And we've got the number of pumping strokes this time is what? Is 15. Take note, the previous case, we had not pumping stroke, it was just per stroke. We just took like a 1. So we understand that, remember, this VRAM here does not have, in this case, this VRAM does not have this height that was moved here. All right. Like we calculated this out of this VP, per stroke, not when it was 15. So meaning to say, this VRAM here is our actual value. This is the actual volume, right? So in order for us to obtain the volume, now we have to multiply by the number of pumping strokes. Remember, we used VP to calculate the actual volume in that case. All right. So in actual sense, we are calculating like this is VRAM, but this is like actual volume. In our calculation, we are using like the way we take the formula for VRAM. All right. The same way that we use, but take note what we're using here. What was this taken from? From VP. Whereby VP, I say this is an ideal value that you are having there. It's an ideal value that you are taking. So now the actual value is this, which is the volume. So, but the actual value here is taken per stroke. It was calculated out of per stroke. What about the one after we've got 15 pumping stroke? That is the question. So it is going to be like this. We are going to obtain something of this nature. Remember, what we want to calculate is the distance moved by the ram. So that's 5.12. So in this case, the distance moved by the ram, we are going to take it from this case that the volume that we are going to have from the ram is going to be equivalent to the V dissipated by what? By the piston, which is the V dissipated by the piston. All right, dissipated by the piston. So this is the idea that we are talking about here. I want us to understand this because there is the VRAM that we are supposed to calculate from area times the ram distance. That's pi d squared over 4 times the ram distance. So this is our area, cross-sectional area. But because here we are now at the actual condition, we are using actual values. So we are going to take the actual value that we had times the number of pumping strokes. It's a continuation. Instead of you taking the old value, you use that old value with the VP to find VR. This here gives us exactly the actual values that you're given. Remember, VR is equal to VP. All right? Are we together? VP and VR are the same. So if they are the same, therefore we can calculate our H from this because we have got the actual values here that we had before. What we need is this H. So we can just divide this side. So H is going to be equal to the actual volume that we had, 5,308 times 10 to the exponent of -4 times the number of pumping strokes. How many pumping strokes are we given there? 15. So we're going to multiply by 15 over what? In this case, we have to consider, sorry for that, we have to consider that we want H. So we are going to divide by this pi d squared for the area. So we are going to divide by pi times d squared. Remember the diameter from the ram here. We have got the diameter on the ram 0.35. We are using the ram, the one on the ram 0.35 squared over 4. So this is going to give us the distance moved by what? The distance moved by the ram, that's 0.08275, something like that, which we can just write as 0.083. All right, 0.083 in meters. That's our H. All right, which is the distance moved by what? The distance moved by the ram. Right. So you see how questions might be given as they just want you to manipulate your formulas. All right. How to manipulate the formulas. Okay, this is what you are being tested. Can you be able to manipulate the formulas? That is the question. Are you able to manipulate the formulas when given such type? Okay, so checking on this part, 5.2 is just to name 2 functions of hydraulic accumulators in this case. All right, so we are given to name 2 functions of hydraulic accumulators. So I just want you guys to have one of 2 of these part that I have got here so that you can just check 1 or 2 to add from what you understand or from what you already have. So we can use them to provide reserve power to supply oil for high transient flow demands, provide sufficient power to complete one or more cycles of operation of the equipment. If the equipment doesn't work, to help reduce pump ripple, act as a hydraulic shock absorbers, and may be used as a primary power source for small hydraulic systems. All right, so that's where we can be able to apply this or to use this in our industrial applications. All right, that is the functions of what? A hydraulic accumulator. Then on 5.3, which is the one that has to do with the hydraulic accumulator, there we are given an accumulator. A mass-loaded, that's a mass-loaded accumulator, yes, a diameter of 420 millimeters. So we are given a mass-loaded accumulator. All right, that has got a diameter of 420 millimeters and a mass of 520 is to applied. So remember, when the accumulator is loaded, this mass that you're talking about is the one that is affecting the ram. So also this is the diameter on the ram. All right, that's 5.3. So you'll be given the diameter on the ram. Divide by 1,000. That's gonna be 0.42 meters. Then we have got the mass, which is the mass of the ram. In this case, that's 550 kilograms. And the machine saves to the machine. Requires, all right. The machine requires a pressure of. All right, there's a statement that is not well there. All right, so if it saves, it then requires a pressure for that to be what? 1.5 megapascal. So we have got the pressure exerted, that is the pressure needed, 1.5 megapascal there. Calculate the additional mass, which is the mass required, which is an additional mass to act as a weight to obtain the required, which is this one, that it must serve. All right, so it must have this pressure. So in order for us to have this pressure, there is an additional mass required to have this pressure. So where do we have this mass? Remember, I told you guys from the total pressure that you, because it must save, it must accommodate this pressure. How do you calculate pressure? That is the question. Remember, the pressure is simply the force times the force over what? The force over area. Whereby in this case, we are simply talking about this force. In this case, if you cross multiply, it's going to be force is equal to the pressure times the area, and the force is equal to the mass, which is the total mass times the gravitational acceleration. That is the one that we have there. The total mass is equal to PI, pressure times the area. So in order for us to have the total mass, we're going to divide by G. So that means the total mass is equal to the pressure times the area over the gravitational acceleration. This is going to give us the total mass. And from the total mass, we use it to calculate the additional mass since we have got the mass of the ram. All right. So this one is just a continuation. Remember, the area is given by pi d squared, which is the area on the ram, pi d squared over 4. So this is pressure. Remember, our pressure there is 1.5 times 10 to the exponent of 6 times the area, which is pi d squared over 4. So that's pi times the diameter of the ram, 0.42 squared over 4. So this was a straightforward question. We have talked about this over the gravitational acceleration, which is 9.8. There we obtain the total mass. So our total mass was going to be what? It was going to be something like, where did I write these values, guys? You see these things of preparing this and that. So you're going to have something like 21,205,7502, 3 decimal places. All right, this is the mass. That is the one that we are having, the total mass. Okay? But remember that the total mass is a combination of these two, because this is the total mass. So there's no way these two should give us the total mass. All right. There's no way, boss. This is this is the total. So if we add in this case the mass, that is the mass which is our total mass to be equal to the mass of the RAM plus the additional mass to be added. In this case, we can be able to calculate the additional mass because we want this additional mass. So you just have to subtract from the total mass. We have to transpose our mass from the RAM and subtract it from the total mass in order to obtain what? The additional mass. That is the condition of your question. And it shall be like that. So the additional mass in this case, all right? The additional mass in this case is going to be the total mass, which is the one that we calculated from the total pressure. That is the one that is supposed to save, to accommodate. All right? That's 0.75 minus the mass from the RAM. We are given that the mass here of the RAM is 550 kilograms. So that is 550 kilograms. So if we subtract this, we obtain the additional mass in order for us to obtain that pressure. That is the idea of the question. That's 20,655.75 kilograms. That is what you're supposed to have as the additional mass. Okay, just like that. Just like that. So guys, I advise you to work with more questions and introductions. We talked about these introductions, so revise as much as you can also. 5.4, where we are given, in this case, a water pump. That's a pump. So we're given a hydraulic pump, a single acting 2-cylinder pump. So you're given the number of cylinders there. C is equal to 2. It has got a plunger diameter. Remember, when you're dealing with a water pump, you should be dealing with the plunger. All right. So the diameter of the plunger, that's 0.08 already in meters. And a stroke length, the stroke length convert to meters. This is 75 centimeters divided by 100. That's 0.75 meters. If the efficiency of the pump is 90%, so there we have got the efficiency of the pump, which is 90% at a pressure of 1,050 kilopascal. So a given pressure 1,050 kilopascal. That is what you're given there. Calculate the power to drive the pump at 680 revs per second, given the speed in revs per second of 680 revs per second. What is going to be the power to drive the pump, which is, in this case, we say this is referred to as Pn, all right? So from the efficiency, remember efficiency is given as what? I talked about this also, that efficiency can be taken from power, P out over Pn times 100%. It can be taken from work done. It can be taken from volume, but here we're talking about power, all right? So Pn, which is the power to drive the pump. We are talking about the motor in this case, the one that is to drive the pump. So considering this, we are going to see that P out can be calculated. We can calculate this P out from work done per second. Remember, we've got actual values now since we've got efficiency. So we can calculate our P out in this case from the we can calculate P out from what? From the work done per second. Remember, the power is simply work done per second. But the work done per second, where is it taken from? The work done per second is taken from where? This is taken from work done. Remember, your work done is taken from the pressure. We've got pressure here times. We also have the volume total. We can calculate the volume from these three. We can have volume from these three. All right. So times the volume total. All right. So this here gives us the work done. But in order for us to have work done per second, it means we must have work done, which is pressure times the total volume times the speed in revs per second. I explained also this one on the hydraulic pump. Okay, times n revs per second to have work done per second. We have joules per second, which is power. But what about VT? Like I said, we have to calculate this from these three. The number of cylinders, the diameter, and the stroke length. We can calculate our VT. Remember, the total volume can be calculated. VT, the total volume, is simply equal to the area, the cross-sectional area, times the stroke length, but we have to consider the number of cylinders also, all right? So meaning to say we can calculate VT from there. That's pi times D, which is 0,8. That's 0,08, sorry, 0,08 squared over 4 times S, which is our stroke length of 0,75, times C, the number of cylinders, which is 2. So this is going to give us the total volume. That's something like 7,5, 398, something like that, times 10 to the exponent of -3, which is gonna be, all right. That will be something like 7,5354. All right, 7,54, not 5,54, but 7,54 times 10 to the exponent of -3 in what? In cubic meters. That's our total volume. So with the total volume, we can be able to calculate P out, that is the output power, from the pressure that you are given, 1050 kilopascal times 10 to the exponent of 3 times the total volume, 7,54 times 10 to the exponent of -3 times n, the number of strokes. Sorry, this is for power. Volume per second, this is not, this is the speed. Let me just put this, the N for speed, like that. So this is the speed, revs per second. So it's going to be 680 in revs per second. Remember, this must be in revs per second so that we obtain joules per second, and joules per second represent what? Represent watts. So that is calculating power, because this is in revs per second. When I have joules per second, that's obtaining power, remember. So this will be something like 5,383,560, something like that. We are going to obtain 3,58560, like that. That is what you're going to obtain in watts. And we can convert this to megawatts. Is it 6 here? 3, 6. So you're going to divide by 1,000 or multiply by 10 to the exponent of 6. That's PO is going to be 5,384 megawatts. Okay, that's what we are going. 836, not 834, guys. Where am I taking the 4? This is 836 5,384. All right, it's gonna be like this here. It's actually 53. There's a value that I missed here. 5,383 560. 5,38356. That's 2, 4, 6. So it's gonna be 5 comma like this, 5 comma here, 84 megawatts. So I took this one wrong. It means I took this one wrongly on my preparation. What I'm just gonna check here before you conclude is to confirm this, because I was preparing this and I just had taken it another way. Why am I having two calculators here? I need one. That's 1050. All right, 50 here times 10 to the exponent of 3, like this, 7,54 times 10 to the exponent of -3 times 680 revs per second times 608 revs per second. So that will be 5,383,560 exactly. So this is the one that we are supposed to have. Then we multiply by 10 to the exponent of -6, like this. So that will be 5,8, like that, 5,84 megawatts. All right. So guys, am I even showing you the screen? All right. This is it, guys. I want you to see this from the screen here. All right. So this was gonna be 5 comma this one. Okay. Very sorry for that, guys. Now I'm tired. Maybe because of that. Okay. See, guys, these things of recording. But anyways, that's our power out, this one. Okay. Then we have to take this into consideration now to say that we have it like this, and to our efficiency, that is our formula here. I listed this formula before. So our efficiency now, we have got 90%. Just remove this. That will be divided by 90. 90 divided by 100, that's 0.9, is equal to P out, which is the one that we are given. We got 5,384. That's 5,384 megawatts. So it's going to be 5,384 megawatts over PN. Already we have used the 100 here by dividing to 90. So we're going to cross multiply, and that's 0.9 times PI. So we divide that by that. So it's going to be 5,384 megawatts divided to what? 0.9 instead. All right, so that's it. Instead of you cross multiplying, we write 0.9. Yes, it's fine. I'm not saying it's wrong, but you can just simplify that direct as it is. All right, so from our calculator, remember this is in megawatts. We wrote this value in megawatts, and it's given as 5, that's 5,384 divided by 0.9, like this, divided by 0.9, which is going to be something like this, 5,982, 5,982, 5,982 in megawatts. Definitely this is also going to be what? In megawatts, since the previous one was given in what? In megawatts. Okay, so yeah, we can have values like this, but what the idea there is we have to apply the efficiency, and we have to consider also the speed, how it is given, because we are supposed to have joules per second, work done per second, power, that is work done per second. So by having power, work done per second, we've got P out, then we can use our efficiency now to calculate the other power that is remaining. That's how we can have these questions just direct and straightforward. So let's hope for more questions to come from Maison African Motives.